Okay, so hello everyone again. I think we can now start. Um, so today's webinar is about designing durable products using SimScale, generally using FEA, why you should use simulation, and especially why you should use SimScale for that. We won't talk about too many technical details. We'll see it rather from a process point of view. So how does a usual design process work without simulation? What are the benefits of using simulation? And even more, what are the benefits if you would use simulation with SimScale? So first, a short note about me. So my name is Richard. I'm here at SimScale, senior engineer. My background is applied mathematics. And in the field, my specialization is in the field of structural mechanics, so FEA, finite element analysis. Okay, so let's talk about designing products. So I guess the audience today is split between designers and engineers. So let's talk first about designing. Why is designing a complex process? So first of all, we have multiple design objectives and constraints. So that first of all, if you're talking about consumer products, aesthetics is actually the first meaningful objective that without aesthetics, people won't buy specific products since they're not appealing. Of course, this is hard to quantify using simulation. Another important aspect is the actual functionality of the product. So how does it actually fulfill its purpose? Of course, this is a number one criteria that the product should fulfill its purpose. On the other hand, design should be cost effective. So we do not want to waste any money on specifics which are not relevant to the functionality, aesthetics, and so forth. So we want to reduce costs as much as possible. Of course, if you talk about also about consumer products, but not only about consumer products, durability is actually also an important factor. So for example, if we take the example here that you see in the picture, some bike helmet design, probably durability is not a problem if you talk about the helmet itself, because if it crashes once, you should definitely put it to waste, because it's only a one-time basically usable for a case of crash. But if you're talking about, for example, the snap fit of the chin strap, of course, this would need to sustain multiple openings and closings of the snap fit. So durability is also here a very important factor. So you don't want to have a very safe design, very stable, but then some weak component like the snap fit will last only, I don't know, 5 or 10 load cycles. Of course, especially here in this example, safety for consumer products is also a very important factor. So you don't want to put the surroundings or the customers in danger if they use your product. This could be very costly, and yeah, should be avoided in all cases that there could be any safety issues. Of course, for the helmet, you should design it especially for safety. And of course, there might be some certification constraints and objective. So your designs might need to fulfill some test criteria to be able to be sold on specific markets. So if you talk about helmets, could be CPSC or Euronorm norm that you need to fulfill if you want to sell your product on the American or the European market. So there might be many more design aspects and objectives. Talking about these, using simulation, you could at least evaluate 5 of those 6 aspects. So functionality, cost efficiency, durability, safety, and of course certification. If you basically do a virtual certification test and it passes, at least you have a first indicator that the real-life test would also be passed. Okay, so then let's zoom out a little bit and have a look at the general design process. First of all, on top we see the one without any virtual testing. So usually you start with an initial design. The initial design most of the times is based on the last product increment, or you have some best practices, or you have some initial experience you have for your initial design. So the first step after that, if you don't use simulation, is build a physical prototype. In most cases, this is very expensive. It's time-consuming. For certain applications, you first need to build the machining equipment and so forth. So it's probably a very high cost step. After you build a prototype, this also takes some time. You do a physical test. Physical testing is, I would always say, physical test is needed if possible. Also, if you use simulation, you should not skip at least on the final physical test. But without using simulation, the test has to be done for every product iteration, every design iteration, every increment. And then after you did the testing, before the testing, you need to make up your mind actually what you want to test, where you want to get probes, which results you want to get out of the test, to make any informed design decision based on the test. So after you get your data from the test, you do a redesign. And this is actually a very, very big part of a designer's process, that he, from the results that he gets, makes a good decision on how to improve the design, in which direction should you move certain parameters of your design. So this will then again lead to a new physical prototype, which will be tested and so forth, until at some point you say, okay, I fulfill all my criteria, so I can build the actual product. If you use simulation, you still have an iterative design process, but in difference, it's to the one without simulation, it can iterate much faster. So you completely skip the physical prototype. Normal simulation turnaround times are between minutes to hours, whereas for physical testing, it could be days to weeks or even months, depending on what you actually want to test. If it's a durability test where you want to investigate very high load cycles, this could really take weeks to be completed for each design increment. Another problem is, especially if you don't have an initial design where you can derive your new design from, so you're having a very innovative product that no one has on the market, was never built before, usually start with a very bad initial design. So your initial guess is most of the times a little bit off your target. So even more if you're very innovative, have a very innovative design, it's even more important to use simulation, because otherwise you need a lot more design cycles than you would usually use for a product that you designed already for centuries and anyways only change in very small increments. So using simulation, you can do a lot of design increments very fast. Additionally, compared to the test, you know your results on any given point on your model. So you don't have to think very long before the test actually where I want to get my results, where do I put my probes, my sensors, what do I measure, so forth. You basically, after the simulation, have the complete knowledge of all on all possible data points that you can imagine. So the cycle gets very quick, and you get a lot shorter to a stage where you can actually start building the product, and it's also more cost efficient than in a traditional process. Okay, so this is one reason why you, if you can, should not skip on using simulation for your design process. The next thing is it's not only important to use simulation, but it's also important when do I use simulation. So if I generally without or with simulation, the cost of a design change also depends on at which stage of my design process I will alter my design. If it's very early, I have a wide range of possibilities to which I can alter my design, and it is a still very low cost since I have not much dependencies that I have to change after I made a small improvement on a specific part of my model. Whereas later in the design process, if it goes, if I come close to the product launch, the cost of implementing design changes increases rapidly, and in a lot of cases it can rarely be realized completely. So during my process, I create a lot of dependencies. When later in the stage I want to change even a small part, it's very hard to implement this, and it's also very costly since it will affect a lot of other components as well. So whenever do any design decision, try to do it as early as possible, and with simulation you can even do it before you actually build the first prototype. So this gives you really a competitive advantage because you can from the beginning iterate on your design without even having built any prototype. So, and what means better design decisions? Of course, it depends on the focus that you actually want to have right now, or on the constraints and objectives you have that we've spoken of at the beginning. So, of course, you could try to lower the costs. You can try to lower the failure risk. So, if a customer handles your product, of course, you want to lower the risk to a minimum that the product fails if the user handles the products as specified, of course. In most cases, this goes with lowering the costs, is lowering the weight, but it could also increase the user experience if you have a lighter design. And of course, increasing the product lifetime is also in most cases a wanted feature. Increasing the performance, of course, performance is again could mean a lot of different things depending on your actual application. So if you stay at the example from the beginning, the performance of the helmet could be, for example, how high is the reduction of the impact acceleration for a specific design, or how good is the thermal comfort for this helmet design, how good are the acoustics if I actually drive at high speeds. Some helmets could be very loud, so I cannot speak with the partner where I go to bike with. So this performance could mean a lot of things. All of them could be evaluated using simulation. And of course, designers and engineers might have also might focus on different aspects, and also sometimes are in different stages of design process. So a designer, for him, it's probably enough early in the design process to have a rough estimation on the product strength and its durability, and he just want to make sure he can test multiple design variants. For example, an engineer might want to make a final validation of the final design before he puts it actually into a certification test. So also the roles play a role here. So now we learned why we should use FEA or computer-aided engineering at all, and why should you use SimScale for that. So if we see, okay, there are so many benefits using simulation, why isn't everyone already using simulation? So in this, there are mainly three reasons. So first of all, the software is not accessible. Traditional software needs to be installed locally. It needs a lot of hardware, a lot of upfront investment before you actually can run your first analysis. Depending on the tools you use, you need, or the application you use, you might need a small cluster on your office, which is a few €1,000 before you even can get any return on investment on this. So SimScale changes this because it's just accessible via web browser. It's agnostic to your operating system. So traditional tools mainly run on perhaps Windows, perhaps Linux, perhaps Mac. Most of them don't run on all. For SimScale, this is a non-issue. So whenever you have a standard web browser, you can access SimScale, access all the simulation power that we have and that we deliver to you via web browser and via the cloud. So usually if you run your analysis locally, this fills up completely the usage of your local hardware, so you cannot work while the computation is running. For SimScale, it's completely different. You can run 1 or 10 or 100 simulations at the same time, and there's absolutely zero workload on your local PC. All the computations are carried out on the cloud. When the results are done, you get an email, you log in, and you can post-process the results. Another thing is the licensing model is flexible and it's very cost efficient for SimScale. So you start with a professional plan for about €200 a month, so $2,400 a year. And with traditional software, it is not really reachable. So you start at about €10,000 or dollars. And finally, this traditional simulation software is made for experts. It's made for engineers who are specified in numerical analysis, and not for the everyone, the designer or someone who's not an expert in numerical analysis. With SimScale, we changed that with having, first of all, very intuitive UI design. And additionally, we have a public project template with over 40,000 projects where you can use the knowledge of other people to create your own analysis and learn from others very efficiently. So all those public projects can be imported into your own workspace. You can review how someone else had set up his simulation. You can simply exchange your CAD model, reassign the boundary conditions, and simply run it without having to know too much upfront on simulation. Additionally, we have something that you would never have with traditional software, with live support. So whenever you get stuck in your project, you simply write to the support agent that's currently available, pose your question, and you can immediately answer your request. So you don't have to wait a day or two for the email of your support provider to get any information on your problem, and you don't have to send around gigabytes of data for someone else to have a look at your project and tell you actually what went wrong. So you can quickly share the project with the online support. You can have a look directly in your project and tell you where the problem is. Okay, so these are the three main factors why you should choose SimScale over traditional software. The workflow is essentially the same that you would have in a traditional CAE software. So you start with the import of the CAD model, you mesh the geometry, you create the simulation, you run it, but not locally, but on our computing centers, and in the end you can also online post-process your results without having to download any of the files locally to your hard disk. Of course, we have not only structural mechanics, we have a lot of detailed analysis types here for structural analysis. You can do static stress analysis, you can have a transient dynamic analysis, and also thermal stresses and harmonic vibration and lots more, eigenmodes and so forth. I guess I forgot to tell something about the questions. So whenever you have a question, we'll try to do them at the end because we're not sure if we can make it in time. We're already pretty late. So if you have a question, ask at the end. I'll try to answer them. So besides solid mechanics, you have also different types of physics that you can simulate with SimScale. You have fluid dynamics, everything that is associated with any flow phenomena can be analyzed, thermodynamics, and also particle analysis. I already mentioned that before, so SimScale has the world's largest database of simulation projects. Currently we have over 40,000 different projects where you can review the setup and learn from them. This is a very good resource of learning specifics either about a specific application or actually how to model it using finite element analysis or CFD analysis. So let's do an example on to really see what we're talking about. This is an actual case that is also a public project on SimScale. So the case is as follows. We have two different possible designs of a wheel for a kid's bike. One has 5 spokes. This was the initial design, and then there is a proposed improvement which saves some weight using only 3 spokes. And now actually the problem is how do we evaluate how good the design is or not. So of course we could now model a prototype, which is, again, could be very costly. What we do now is we just simulate both and see which one performs better. So actually, how do we assess if a design is actually lasting longer or not? There are different criteria how you can assess if your product is failing after a specific amount of time or a specific number of load cycles, or after it is applied a load of a specific magnitude. So we want to investigate 2 different values here that could be of importance. First of all, of course, if it's a usual load case, loading or someone sits on the bike and tries to ride it, the wheel should not permanently deform. Not only for wheels, but for most of any consumer goods, it's not desired that you have any permanent deformation after usage. So how can I know if there is any permanent deformation? Usually, if you talk about ductile materials like steels or also most types of plastics, there's something called the yield limit. If I stress the material beyond this limit, the deformation that I get will not be 100% reversible. So I end up with a portion of a permanent deformation. So in this case, yield limit could be around 21 megapascal. So this tells me if a single time load would actually already have such an impact on the product that it's basically not usable anymore and it failed already. So this is basically a catastrophic load case that we want to have. So some extreme loading should that should be resolved by the application should be withstand here. The next thing is Now, I of course don't want only one rotation of the wheel. Of course, I want to have multiple thousands, millions. So how can I know if basically my wheel will never break due to excessive like number of load cycles? For most materials, you can have something like that's called fatigue limit. So, or there's also another thing called endurance limit. They're similar, not exactly the same. So, if you have for your material a fatigue limit, it basically specifies that if your load cycle, so a single loading, doesn't exceed the stress of this value, then you can have almost infinite number of load cycles, and it will not degrade the strength of your material. This infinite number is that, of course, not infinite. For most materials, it's about 1, 10 million, 5 million, 500 million, depending on who defines that. But it's a significant amount of load cycles that even with the bike wheel will not be exceeded. So actually, we want to do a simulation and check our stresses if they will exceed these limits or not. And if they don't, then we can consider this actually at least the long-time fatigue is ensured for those designs. So we have two different load cases here. First, we have a radial load with about 35 kilograms, and we have a lateral load with about 7 kilograms. So it's an not a kid sitting on it, but perhaps some dynamic load. If you're driving on a bumpy road or so, dynamic loading can exceed the static load, the static weight, by a multiple. So this makes sure with 35 kilograms that a kid of about, I don't know, 10 to 15 kilograms, still on a very bumpy road, has about this maximum load here, and lateral load similarly. So if you drive in circles. Okay, so now let's see how we can do this on SimScale. So you go on the website, simscale.com, you log in. I'm already logged in. So what we have already told about is the public projects, but also we have your own dashboard with your personal projects. When you're a professional user, you see those little marks here. That means you have a private project. If you're a public or a community user, all your projects that you create are visible to others, and they can use this to learn from your simulations. So I opened this project. It's actually already finished, but I just want to show you how this would work. So here we already have the geometry. If you want to change it right now and use a different one, of course, we can either upload it from our hard drive or just import it, for example, from Onshape. I won't do this right now, but it works as if you would upload it from your hard drive, and even ensures that you don't need any local storage. If you create your model using Onshape, directly import it to SimScale, you don't have any local storage in between. So here we have the 3 spokes design. First thing you would do, meshing. You start a mesh, and that's it. So locally nothing is done. What happens now is computation is started on our on a machine of a computation cluster. The files are uploaded there. Everything is secured, so you don't have to be afraid if you're a private user that anyone gets to see your data or could be in any way get access to your data. Next thing after the meshing is done, depending on the complexity, this could take a few seconds. you actually just create your new simulation run. Depending on the application you have, can be either fluid mechanics, solid, thermostructural particles. In this case, it's a static analysis, and what we do is we assign a mesh to it that we computed, and there it is. You can see how nicely this is meshed. You can also suppress the mesh and only see the surfaces. And then the usual process starts. You assign a material. So we need polypropylene, assign it to our volume here. We add some constraints. In this case, we add a fixed support on the axle, and we add a load of 750 Newton. Let's put it like this. And that's it. So we have the design. So we have the load cases, we have the fixation. What we could do is change to a different machine to run the model on. So for example, run it on, I don't know, 8-core machine. Depending on the size of your model, you want to choose a larger or smaller machine. And create a run and start it. So we're going to speed this up. So if the simulation is finished, the next thing, you're going to go to the post-processor and actually have a look at your result. So we already saved a state on the deformed model. So let's have a look. We're interested in the stresses actually. So let's see if we can get them. Okay, so what we see here, okay, it's still loading. Okay, this shows the displacement. Here we can change different fields that we want to visualize. So in this case, this is the stresses, the equivalent stresses that we're going to see here. This is the absolute value, and when what we see here is that the maximum value here of 28 megapascal actually exceeds our fatigue limit. So this design would actually not pass our fatigue test. And we can also see focus on actually the areas where this fatigue limit is exceeded, and we see, okay, the bending is pretty prominent here, so there need to be an improved situation for this bending here, and also we have some stress concentrations also in other parts. So let's go back to the presentation. I've got to speed things up here. So we got the results. We see different zones where our design needs to be improved. The 5-spokes design actually is fine. It is not exceeding the fatigue limit. Also on this view we don't see it. For the lateral load, which we didn't use right now, we see also a certain spot where the fatigue limit is exceeded, but this is not actually the problematic load case. And so if you summarize the results, we see that the 5-spokes design actually passes our criteria, and the 3-spokes design not, because it plastifies and it also doesn't fulfill the fatigue limit. So then this is the point where again the creativity or the experience of the designer comes into place to decide actually how can you improve the design. So for one option could be I increase the outer ring width or thickness by 1, 2 millimeters, 3, I don't know. So since it's online simulation tool, I just create quickly 3 different models, run them, and can easily assess which one will fit our design criteria. If I would now need to create a prototype, either I build 3 different ones, or I put my bets on one single prototype. Either I can win and it fulfills the criteria or not, and I basically wasted a lot of money. Design option 2 is changing material. Of course, I could use higher strength material. In most cases, this is not easy since this increases the cost dramatically. In some cases, I couldn't just change the material since there are other restrictions which yeah, I have to obey to use the material that is already defined. So quickly wrap it up. Why we use FEA? So first we make better design decisions and we make them earlier in the design process. Why using SimScale? Because it overcomes the three main barriers that you would have with traditional FEA: accessibility, the cost, and the expertise that you need to have in for traditional tools to be able to run your analysis. Who can use SimScale? Of course, not only engineers, not only numerical analysis specialists, but also pure designers. Okay, how to start? I showed you. Go to simscale.com, sign up, and test your models. Okay, so we're through. Let's go to the questions. I think we're already over time. So if you don't mind, you see my email address here. If you have questions, just ping me, write me an email, and I'll try to answer them as soon as possible. If not, then thank you very much for being part on this webinar today. If you follow us, there will be in the upcoming weeks more of these webinars, this short 30 minutes webinars. If you like them, then tune in for our next sessions. And thank you very much again for having me, and hopefully you try SimScale and experience its benefits. Thanks again, and bye-bye.